very happy to have Sophie Libkind, who will be celebrating a happy birthday to Algebraic Dynamics.
Yeah, thanks, Paul. Yay. So, Algebraic Dynamics is a Julia package in the Algebraic Julia ecosystem for applied category theory that I've been working on for a little over a year, and I think it's about celebrating its first birthday. So I wanted to do is just sort of give a tour about what is algebraic dynamics, and in particular we'll go sort of through its two sort of main modules, and then those are what I think of as like oldies but goodies, and then if we have time, two cool new things that are up and coming. So this seems like a great way to celebrate a birthday. So first of all, what is algebraic dynamics? So I think of it as a Julia package for operad algebras of dynamical systems. In order to sort of tell you about algebraic dynamics, we have to start with like, what do we mean by operad algebra? And something that I think is really cool about algebraic dynamics, and in fact sort of all of the algebraic Julia packages, they let you sort of do category theory without, it's under the hood. So you can sort of, if you don't know anything about category theory, you can still pick up this package and start playing with it. But I do want to give sort of a rough overview of what is an operad algebra so that we're all on the same page. So to me, let's start with so an operad algebra sort of has two parts. It has an operad, which I'll call O for us. And often we talk about this as describing some sort of syntax, or how do things compose. And the algebra, so an algebra, if you are a category theorist, it's an operad functor from our operad into the operad underlying set. But more importantly, it gives the semantics, or it tells us sort of what is being composed. And so I think these two, thinking about this as syntax and semantics, or how do things compose, what is composed is really sort of the key distinction between these two halves. And what the math does is make a really nice, clean separation between them, which turns out to be really helpful. So in an operad, so these two things are sort of made up of two different parts. The first is what you might call types, or I also think of these as, when we're thinking about systems, as the interfaces of systems. Some people also call these sorts or objects, so a lot of ways to think about this. And then the second component is thinking about, so this sort of tells you about one thing, but we also care about many things together. That's what composition is. So we have types. We might call these things terms. We speak about them in a number of ways. You might call them arrangements. We often talk about them as a diagram of systems. Or I think the way I'll talk about them the most today is as composition patterns. OK, so to sort of give an example of this, I want to use my favorite non-math example, which is of Mad Libs. So let's first talk about our operad, or like how do things compose. So what are the types of things? Well, they're sort of like parts of speech. Oh, I'm going to try and color code today. So I'm going to try and use purple for my types. So we have things like nouns, things like verbs, things like sentences. So those are sort of my interfaces, or my types. And now I want to say, like, what can we compose? So what can sort of fill in a verb? So what could I put here? It's the set of, like, all English verbs. So again, these are like, what is the type of a verb? It's a verb type. So maybe that's a little silly, but we'll see how that helps us with our dynamical systems in a bit. What are the arrangements? Sort of how can we arrange these types of things? So in Mad Libs, if you've played this game before, it goes like this. I can say something like the noun, that ate my noun. That's a thing that takes two nouns. So it's a map from noun, noun, and it gives me back sort of a new noun. So noun that ate my noun.
The Mary that ate my sandwich is a noun.
A noun phrase. Noun phrase. We could make this more complicated by saying adjective noun or something like that. And then the idea about, so what does the algebra tell us? What is the semantics? It says, if I fill in each one of these, I should give you a new noun phrase. And so, does anyone want to play the game? Brenda, do you want to give me an adjective?
Red.
Red, a noun. Apples.
Banana.
Oh no. All right, we have a very silly sentence, or a very silly new noun phrase, the red apple that ate my banana. And so what sort of goes in this box is the rules of composition, and in our case, it's the game of Mad Libs. Okay, so I have obviously not been talking about systems, or dynamical systems. I've been talking about words and sentences. But sort of for the different pieces of algebraic dynamics, we'll fill in this table and then sort of look at examples of it. So I'm going to erase. Any questions? You enjoyed the sentence? Cool. All right. So let's see. Algebraic dynamics is like first skill is resource sharers. And resource sharers is what we often call a UWD algebra. These are equivalent to sort of co-span algebras. And so let me tell you what they consist of. Sorry, I'm back over here. So our syntax, our types of our systems are going to be a number of exposed ports. So here we have like m exposed ports, and that's a finite set. And then you have to say, OK, now we're about to finally get to dynamical systems. What things can I fill a system of this type with? So what kind of system can I put in this box? Well, the things to fill that box, I need a set of states, so finite set S. I need a vector field from RS to TRS. And then I also need this is an open system. It interacts with the outside world. So I need a port map that assigns to each exposed port a state that it exposes. So, so now I've told you, these are the types of the systems, and this is sort of what they are. This is the contents of the dynamical systems. And so then what about how they interact, which is sort of why we're here, perhaps. So here we need to tell you, given systems of type 1, M1 through Mn, how can I give you a system of type n? And so my picture here is if I have interfaces like this. So this is like my M1, my M2, and I want to turn it into a big system of type 3. What are the rules for how to define an arrangement of these? And the rule is I'm going to give you some junctions. And for each of, I call these inner ports, I'm going to assign them to a junction. Whoops. And each of the outer ports, I'm also going to assign to a junction. And mathematically, what this is a diagram of finite sets. So we have our, let me draw it. This one's always the biggest one. OK. I'm going to draw it here. So I have my some finite set of junctions, all of my ports from my sort of domain systems, my ports from my codomain systems. Each of those gets assigned to a junction. And I'm also going to keep track of my boxes. So I have my n boxes, and I'm just going to say which inner port came from what box. So this is my that's how I define an arrangement. And now the question is, if I fill each of these with an appropriate system, I need to get back a system of sort of the outer type n. And the slogan for how to do this is you identify states attached at junctions. Attached at junctions. And we're going to add their dynamics. And we'll see an example sort of why this slogan makes sense. All right. Any qualms? OK. So
when you say state,
Yeah.
you're more thinking of like dimensions of state.
Right. So when I say state, I should really say like state variable.
State variable.
Is that okay?
Yeah.
It's the elements of set S.
Right. Elements of the set S. Sweet. Okay. So let's go to, I have so many pens. Let's go on to maybe our first example. And so often so this is going to be of a compartmental epidemiology model. And the first thing we're going to do is define our primitive systems. Whoops. So I'm going to have, let's see, what did I use? Purple. OK. So I'm going to have a system that corresponds to, I'm thinking of it in my head as infection. It has, the interface is it has 2 exposed ports. And then its filling, its dynamics, is I'm going to have 2 variables, S and I. So I have 2 of these. Now I need to give you my vector field. So S dot is going to be minus beta times SI. So the susceptible population is shrinking depending on interactions between susceptible and infected people. And all those susceptible people become infected. So my I dot is beta SI. Lastly, I need to tell you a port map. So I'm going to say this port exposes the susceptible population. This port exposes the infected population. Sweet. OK, so that's primitive system number 1. And now we're actually ready to see some code. So here we have a continuous resource share. So we're in resource sharing world. Float 64 means I have like S and I. That sort of corresponds to the fact that I have R written here, floating point numbers. It has 2 ports. Yep. 2 states. Yep. The dynamics that I told you about. And then this tells us about the port map. So I really implemented in algebraic dynamics exactly this picture. So this picture is rigorous mathematically and implemented in code.
So beta must be above.
Yep, beta is like a parameter that when I want to create this like thing, I need to feed it a beta. Yep. All right, let's do another primitive system. This one also has 2 states. Oh, also has 2 ports. And it has 2 states, R and, oh no, whoops. Well, yes, but it has I and R. What are the dynamics? I decreases at a rate gamma I. R increases at a rate of gamma I. What gets exposed? An I and the R. And so as I've drawn here, these are like 2 separate systems. There's an infected population that's growing, an infected population that's interacting with susceptible people and growing. And down here I have like a totally other infected population where they're recovering. But what we want to do is really couple these and say, hey, those are the same infected population. So we sort of did up here. Now we're ready to add in some composition. But before I do that, let's just see that, in fact, we have, similar to our infection model, a recovery model.
How are you encoding that with the bijection between the M and the S? Where's the P map?
It's this thing here, this 1 to 2. It's a vector 1, 2, which says the first P goes to the first state variable. The second P goes to the second variable. Yeah.
So they both took I would be 1, 1.
Yep. Sweet. OK, sweet. So we're on to defining the interaction pattern. And it turns out I don't need this. So that's going to be our new system is going to have 3 exposed ports. That's our N. Now I need to tell you a number of junctions. I'm going to have 3 junctions, 1, 2, 3. And I have to tell you how these all hook together. The S is going to map to this junction. Both I's are going to map to that junction. The R is going to map to that junction. And then they all get exposed. And this is now implemented in CATLAB. This sort of thing is called a UWD, or an undirected wiring diagram. And CATLAB will not only do you have some nice syntax for generating this thing, but it also produces a nice visual of it. And you can sort of check with your eyes that that picture is quite a lot like the picture I have up here. All right.
Can I ask another question?
Yeah.
What if you wanted to get rid of the you don't want to see the eyes, let's say?
Yep.
Would you erase that? Like, what would that be?
That would be, I think instead of where I get rid of this I, and then I'd say where SIR begin. And that would allow me to say, like, the S and the I are getting outputted, but I care about I because I need to use it inside. Yep. All right, so finally we do the composition, and we can tell you, I'll tell you what the composition is. So the rules are identify state variables attached to junctions. So S, not attached to anything. I, both of these are attached, so now I only end up with one I population. R, all on its own. What are the dynamics? Well, the S and the R are going to be the same as before. Wow. And then the I, the rule is add the dynamics. So for the I dot, I'm going to have beta Si minus gamma I. And again, I'm outputting these things on the wires. So now that sort of makes sense of what we mean by this. OK, how does it look in algebraic dynamics? I say O apply. So to the composition pattern, in the infection box, I'm going to put the infection model. In the recovery box, I'm going to put the recovery model. Seems reasonable. And then we can solve and graph it. And indeed, we get a very reasonable looking graph of the susceptible population is the blue curve. The infected is the orange one. And the recovered population is the green curve. And this is what you expect to see. So great. All right. So that is my first example. Oh, and then I wanted to say, yeah.
Does that graphing use any of the compositional structure to solve this ODE?
It doesn't. That's a great open piece, which is that right now, algebraic dynamics only sort of does the composition. But it does make sense that you should be able to say, hey, I know it's done in these pieces. Can I solve some subsystems and then glue the results together? So that's definitely an area for future work.
So this ODE problem, that's just a function you're calling or something?
Yep. Yep. Cool. All right. So I also wanted to say that one of the great things about operands and operand algebras is you can define things hierarchically. So we could say, suppose I have another model. Well, let's see. I think first we're going to do the composition pattern. So here we have, I'm going to draw it small here. So here we have now 4 outputs. We're going to have 2 models. One I'm thinking of as my SIR. One I'm thinking of as this, what do I call it? Mortality. So it has sort of an R. This is mortality. This is SIR. And now we have junctions which say sort of my S population is the same, my I population is the same, the recovered populations from the 2 models match, and the D population is all on its own. And then what models can I put in there? So I need to define new mortality dynamics, which is going to say I have 2 states, R and D. R declines at some rate minus mu R, and then those get absorbed into the D population. And then what's going to go in here, I'm just going to slap that thing that I already made in there. So I define my new model as mortality dynamics. And then here I'm saying, what am I going to do to this new composition pattern? The SIR model, I'm going to do that SIR model that I composed. And in the mortality box, I'm going to add my new mortality model. So this is really like a hierarchically defined model. And then again, we can solve and plot this. And we get now, you see this D line is rising a little bit. Cool. All right, so that is resource shares part 1. And part 2, I was really excited to put together some examples that have to do with mechanics, because there's been lots of, I don't know, work there. Like, you could compose coupled springs or whatever. And it was exciting to actually do it in algebraic dynamics. So let's go to example 2. Okay, so first, let's think about what one anchored spring is. So the picture is, I have an anchor, I have a spring, it has some spring constant k, and it has a mass of m. Okay, so let's sort of think about the top row. What dynamics is it? So I'm thinking of this as a box with two exposed ports. And what goes into this box? We're going to have 3 states. I'm going to call it m for mass, p for position, and v for velocity. What are the dynamics? The mass doesn't change. The position changes according to the velocity. And how does the velocity change? Minus k p over m. And this is, I am extremely not a physicist, so if you have qualms or questions, let me know, but I probably won't be able to answer. Okay, cool, so that's our anchored spring. Let's go ahead and implement that. This should be sort of old news by now. Here's an example sort of that David was talking about, because here we have like, oh, I forgot to say, what gets outputted? Only the mass and the position. So here we have sort of this hidden velocity inside. Okay, we can make an anchored spring. We can solve and plot the dynamics. Ooh, okay, we see oscillation, which is good, but like also that's not very descriptive. So we can animate it, also using Julia, and we get this cool spring. All right, so let's do some composition. So this is a spring operating in like space or something. There's no gravity here. So let's say, what would happen if I wanted to say, hey, this spring is actually on the planet Earth, and I want to act on it by like gravity or whatever that is. So let's try to come up with a system that represents gravity, or the effect of the Earth. So that thing is going to have just one exposed port. Boom. And its dynamics, it's going to have 2 variables. Again, so let me say this again. This dynamic sort of corresponds to this picture. This box is going to correspond to sort of this picture, sort of the mass and the Earth together. So I lied. It has 2 exposed ports. It has 1. And it has 2 states, a position and a velocity. The position changes according to the velocity. The velocity changes according to gravity. Sounds reasonable? What do we expose? We're going to expose the position. All right, so let's do all that. So an anchored spring with gravity. Here's our gravity model that I just said. Now what we want to do is we want to compose them. And this shouldn't be surprising given how I've labeled this. But we're essentially going to say, hey, these 2 positions, you know, this thing can only be in one position at one time. So I'm going to hook them up. And the mass is just itself. So that's what that looks like. And what are the dynamics that we get? So what does this equal according to sort of this rule? So what are we going to end up with? We have, what variables will we have? We have our mass. We have a position, but that's the same as this position. We have a velocity. I'm going to call that v1. We actually have another velocity. That's a v2. So here, even though these are labeled the same, our diagram doesn't hook them up, so we actually have 2 different velocities. What are the dynamics of all these things? M is 0. v1 is minus kp over m. v2 is 9.8. And what is p dot? I'm going to add the effect of the 2. So it's v1 plus v2. And if you take the second derivative of this, you're like, oh yeah, that is what the acceleration of this spring should be, if you're a physicist. Okay, so let's do the composition. And then to show you that I get a reasonable thing, on the left, I have my original spring, the one I showed you in the last slide, sort of just this. And on the right, I have my spring, which is now being pulled down by gravity. And it's correct that they have the same period. And what's really just changed is that this one, its equilibrium point has been shifted downwards. So, cool. Springs with gravity. All right, more fun with springs. Let's do springs in parallel. So this story is going to be, I'm going to erase and get all of this. So in this story, I have a mass, and now I have two springs with two different spring constants attaching it to my thing. All right, what is my sort of composition story? I'm going to have this filled with sort of, I'm going to call this spring 1, and it's that m, well, you can write it out, m dot, p dot, v dot from before, with the m and the p getting exposed. My second spring is similar, m dot, p dot, v dot, with the m and the p getting exposed. And when I compose these guys, what am I going to do? I'm going to say, well, there's only one mass, so I'm going to hook these guys up. And it can only have one position. And that should give me the dynamics of the system. So let's go ahead and run that. So we have our two springs. We define our composition pattern. We apply our two springs to that pattern. And then, if we solve and plot, we get a reasonable looking thing. That's pretty cool. And even better, so here what I've plotted is the pink is if you imagine just the first spring. The blue is if you imagine just the second spring. This is the composition. And what this one is this is the spring with spring constant K1 plus K2 and the same mass. And in fact, that's what it's supposed to be. So evidence that everything is as I say it is. All right, we'll do one more. I think this one I might just talk through. So these are now thinking about springs in series. So let me draw that picture. So we have a spring with a mass. So this is like K1, M1. We have another spring, K2, with another mass, M2. So the first thing we want to do is define, so we sort of know what this system is. That's our anchored spring that we've been talking about. But now what is this system? I'm calling it like a free spring. It has two masses, it has two positions, and two velocities. So it has a much bigger state space, as we can see, six states. Oh, and here's another example of where I've outputted the mass, the position, not the velocity, then the mass, the position, not the velocity. OK. So let's create those springs. So again, so spring 2, I'm going to attach the position, the first position of spring 2 to the position of spring 1. Same with their masses. And I'm going to leave the mass in the position of spring 2 on its own. Compose. And then, solve and plot. And we get another very reasonable looking diagram. And, OK, so then another sort of sanity check is that if the mass, this mass was 0, so here I've made both of the masses 10. But if mass 1 is 0, these are what's called springs in series. And you should get, so if this is 0, then this is equal to a spring with spring constant K1, K2 over K1 plus K2, possibly the inverse of that. And so we can do that also. So we make the mass 1 very small. This one's our K1 times K2 over K1 plus K2. And we get what we think we should get. Yay. Yeah.
The left animation is very kind of jittery. Is that is that right, or is that a kind of artifact of the plugin?
Oh, that's a good question. My guess is it's right, because my interpretation of what happens when the mass is really small is that it moves very quickly.
Oh, that makes sense. Yeah.
The mass is the thing that pauses it, like makes it move slowly. Yeah. Cool. All right. So that's researchers, the first oldie but goodie. The second oldie but goodie is about machines. So research errors I think of as like an undirected type of composition, because all that's happening is like, you're like, oh, I'm interacting with this lake. And some other guy's like, oh, I'm also interacting with the lake. And that's how we compose. There's no like directedness to the interaction. And then machines is sort of about the opposite, where you're sort of sending messages between different parties. OK, so let's start with back to our board of math, what's going on under the hood. OK, so what are our interfaces? They are going to be boxes, this time with two sets of ports, an input and an output set, both finite sets of ports. What fills such a thing? You need, again, a set of state variables, a update map, which takes in a state and an input and gives you a new state, and a readout, which says, given a state, what is my output?
Should I think of the result of the update map as a tangent vector or as a kind of new state?
So there's two options. So one, you can think of it as a discrete update, where it's just telling you exactly the next state. And indeed, we'll do an example later where we'll put a t there and be like, think of it like a vector field. And in fact, they're implemented identically. Just depends on their interpretation. OK, so what about terms, arrangements? How do I compose such systems? So the story is, if I have some of these guys, and I want to turn them into a big thing, what am I going to do? I'm going to wire stuff up. So let me draw it over here. This is going to be what's called a DWD, or a directed wiring diagram. And I have some finite sets. So I have, oh, I should say this is sort of going from x in 1, x out 1. So these are sort of my inside boxes. And I'm producing sort of this outer box, which has y in input ports and y out outer ports. And so such a composition pattern is given by a DWD, which has y in outer in ports. This is the sum of x in sort of inner in ports, the sum of x out outer inner out ports, and then y out down here. Sorry. OK, and then what is it actually? We also need a set of input wires, which go from these guys to the inputs of inner boxes. So these, I have like 3 of these. A set of wires, which go from the outputs of the inside boxes to the inputs of the inside boxes. I can do things like this. And then finally, a set of wires, which go from the outputs of the inner boxes to the outputs of the outer box. And this is, in fact, a lens in a certain category.
So if I had like 2 wires from the same output to the same other output,
yep.
I guess you're going to tell me what the semantics of that is.
Yeah.
OK.
Sure. What do you do? Well, I'm not going to give you a very satisfying answer. The answer is you send info along the wires. And if you see a split, like 2 things coming out of the same one, you're going to copy that information. And if there's 2 wires going into the same port, you're going to add. And because I'm working in R, that's a thing I'm allowed to do. Sweet. All right. Ready for fun examples? Yay. OK, so let's think about the Fibonacci sequence. OK, so I'm going to define 2 machines. The first machine is going to have 1 input and 1 output. OK, what do I fill it with? I'm going to call this thing delay. What does it have? It's going to have 1 state variable. OK, so I have to tell you what is the update, which goes from given a state, given a state and an input, and I'll call that, oh no, hang on. I like to use U for my state, so I'm going to call that V. Okay, so given a state and an input, I need to give you a new state. And what I'm going to do is I'm going to forget about my current state, and I'm just going to copy what I see. So someone sends me information, I just remember it. And what is the readout going to be given a state? I have to give you an output, and I'm just going to tell you my state. So if you ask me for my information, I'm just going to tell you my state. If you give me something, I'm going to throw away my current state and remember it. And we call this delay because there's sort of this, if you're sending stuff in here, it sort of takes a time step to get it out because you have to remember it and then say it out. That's our delay box. We'll also have this thing called plus, which takes in 2 inputs and 1 output. And this thing also is going to have 1 state. Its update is going to take in, given, we now have, what did I say? Given a state, R, and an input, which is an R squared. Think of this as like X and Y. I need to give you a new state. What is it going to do? It's going to forget about my current state and just add X and Y. So I get 2 things. I store their sum as my current state. The output is, again, just going to take my current state and output it. So here I have 2 very reasonable machines. What am I going to do with them? I'm going to compose them according to this pattern. And CATLAB is great, but sometimes it makes silly-looking wiring diagrams. So let me tell you what that looks like. So I have my ID box and my plus box, and CATLAB has put it on different sides. But the picture is, ooh, I'm going to take my delay, and I'm going to send that as one of the inputs. I'm going to take the output to my plus, and I'm going to send it also as one of the inputs. And I'm also going to send it to the delay box to sort of remember. And then I'm also going to output it to tell the world what it was. OK, and then I claim that when I compose these, so again, to the wiring pattern, in the ID box, I'm going to put the delay machine. In the plus box, I'm going to put the plus machine. And I get a machine which now has 2 states, because there's 1 state coming from here and 1 state coming from here, no inputs, and it's going to have 1 output here.
What does it say, R2?
R2, that's the state space.
Oh.
This is, sorry, so this is only telling you about the dynamics. It doesn't tell you about the output, which would be a good thing to add here. OK, and then we run it. And wow, we get the Fibonacci sequence, just as we predicted. So again, everything's doing reasonable things. All right, so one other type of example I wanted to share was of sort of, as Eigel pointed out, this was for discrete systems that sort of update their state. But you can also think of this V as like a continuous thing, so as a vector field. And then we can compose ODEs in a similar way, where we're sending the outputs of some systems as the inputs to other ones. OK, so for the multi-city SIR model, let's first talk about like what is a single city model going to be. So its interface. Oh no. Oh, well, it's fixable. OK. Except it's going to say it on all the other slides too. OK, so we have a system. It has 3 inputs and 3 outputs. And I'm thinking of this as like susceptible, infected, and recovered people are coming in. Susceptible, infected, and recovered people are leaving. What am I going to fill it with? Unsurprisingly, I'm going to have 3 states. They're going to be S, I, and R. What is the dynamics of the S going to be? It's going to be my original, like if you remember back from 30 minutes ago or whatever, susceptible people become infected at this rate. I'm also, if I think of this as S in, I'm going to add in sort of the flow coming maybe from other cities. And I'm going to subtract off people leaving to other cities. So the flow of people leaving the city. And these are, I and R are going to be the same normal SIR, modulated by this inflow and this outflow. What am I going to output? I'm going to output not S, but I'm going to output mu S to say, like, that's the flow of susceptible people leaving. Mu I, mu R. OK, so that's my single city. And now what do I want to do with it? So here are 3 cities that I've created. These give you the different parameters for infection rate, recovery rate, and the mu, which is sort of like the travel rate. OK, I have my 3 cities. And now I want to compose them according to different systems. So here I have the people from city 1 go to city 2, the people from city 2 go to city 3, the people from city 3 go somewhere, but I don't know where. I can, to that pattern, apply my 3 cities that I just created. And then I can plot what happens. And indeed, for the 3 cities, so blue is city 1, the infection population sort of peaks first. Then city 2's infection population, and then city 3's infection population peaks. So again, a picture that seems reasonable according to our system. And one really cool thing I think about composition in this way, this sort of like division between syntax and semantics, is that we can sort of turn the knobs independently. So I can say, I'm going to keep my 3 cities, but now I'm just going to play with sort of my diagram of systems. So for example, maybe I want to say, now people from city 1 go to city 3 to city 2, and the people from city 2 go back into city 3. And then, oh no. Great. OK. Now we see city 3 now peaks before city 2. Reasonable. And then as another example, maybe I have city 3 is now sort of like an island. People from city 1 go to city 2 and back. City 3 is an island. And so in city 3, no one ever gets infected. Great to be in city 3. Cool. All right. Those are my 2 oldies but goodies. And now we're going to dive into some things that are new and exciting. And OK. Oh, yeah.
What happened if you ran Fibonacci, but with not time step equal 1, but like it would just do a different thing? Like,
not
can
time
you
step.
change? That one was kind of like discrete dynamical system. This one was continuous, and it seemed like you said that the implementation was exactly the same. So in there somewhere is the number 1. It seems like.
Oh, so it's like it just constructs. What happens? It constructs this thing. That's what Algebraic Dynamics does. Then Algebraic Dynamics gives to like an ODE solver, in the continuous case, this vector field. And in the discrete case, it sends it to something called function map, which just does the ka-chunking. So I think that's sort of not happening in Algebraic Dynamics.
Gotcha.
Nice. Any other questions? OK, so as perhaps some motivation, one thing I did not do with my diagram of systems was say, here's city 1. And I want people from city 1 to go to city 2 and to city 3. That's a reasonable thing to do. But if I programmed this exactly, what would happen is, branching like this is copy. So what if every person who left city 1 would get copied into 2 people and go to city 1 and city 2? And that's extremely silly. Doesn't make sense. So we sort of can't, or doing that with Algebraic Dynamics would somehow require the dynamics to know about the wiring pattern, which seems not great. So we want a solution for that. And then as a second piece of motivation, when we talk to epidemiologists and other sort of modelers, they often do care about, they do these really complex computations almost in between the systems. So here we have Micromob, which is for mosquito-borne pathogen transmissions, written by Sean Wu and Dave Smith. And the idea is you exactly sort of like in applied category theory, algebraic dynamics. You have this composition of systems of the adult mosquitoes, the mosquitoes going from eggs to larvae to mosquitoes, and then sort of humans over here doing their humans moving around, going to work thing. And in between you have the blood meal. And the blood meal does not have state. It's just a really complicated, like expert chosen function that says, what is the infection rate given all these people in this area doing this sort of thing and their genetics and the genetics of the So it's like quite complicated, but it's a really important part of the system. And so for algebraic dynamics, or to be useful in this area, we need to be able to sort of represent, be able to sort of put functions in boxes as well. And so sort of something I'm working on, which has been implemented but not yet proved mathematically, which is kind of an interesting place to be in, is this thing called what I'm calling instantaneous machines, although happy for feedback on the words. OK, so what is an instantaneous machine? I'm going to go over here. So the idea is we want to be able to say, here the readout, the outputs could only depend on the state. And I want to say, hey, like, I kind of want the outputs to also depend on the input. That's how we get a function. And so what I'm going to do is type is going to be a set of input ports, a set of output ports, and also a bipartite graph, let's call this E, from whose source are output ports and whose target is input ports. And the interpretation is that if I have an edge from an output port to an input port, that means that the output port depends on the input port, or can depend on the input. Reasonable. OK, how is this story going to change? I'm now going to allow the readout to depend on the inputs. But I'm going to say that this map must factor through only the input ports that I depend on. So for each output, it should really only depend on the ones it says it does. So this is modulo some criteria. I'll say such that stuff. OK, what about terms and arrangements? Almost nothing changes, except we have to be worried about cyclicity. So what you should be worried about is if I drew a picture like this, let's say I'm going to take an x and I'm going to output 2 times x. And then I said, OK, I want to compose this way. You'd be like, OK, Sophie, what's the output? And I'd be like, OK, let me get my input. Well, I need x. Oh no, what's my output? And then it would just keep going. So you would be like very sad. And it turns out that we were talking to people who work on stock and flow diagrams, and they also have this saying, which is something like cycles have to include a stateful thing, which is exactly sort of the criteria we need here. Since this depends on this, we have this cycle that's not broken by a stateful thing. So I believe that this actually comes down to a really nice constraint, which says that, let's see, if I take this thing, these both map into the sum of, whoops, the x in I, whoops, I, sorry, so the push out, basically, the push out of this thing. And here we get a graph where the edges are the wires, the vertices are these, and if that thing is acyclic, we're like good to go. So we need acyclic. And again, we're going to send the information on wires, but we need to do that in sort of the topologically sorted order.
Now I'm lost.
OK, yeah.
What is the topological sorted order and why?
So I have this acyclic graph, and I say, like the output ports I want to, then I can sort those to say that the first ones will definitely not depend on anything after it. And so I want to say I'm going to compute.
Why is that topological?
That's the name of when you sort graphs like this. They're called the topological sort of graphs. I don't know if they have a topology interpretation.
Well, they're contractible.
Mm.
As opposed to closed cycles.
Nice.
But it's not lexicographic or something
Yeah.
like that.
I think also just like, if you tried to do this, you would find out you have to do it this way. Like, I think that's something that's really interesting about coding up this stuff. Is like, it almost tells you what needs to be true here. When you try to do it, you're like, oh, that has to be acyclic. Oh, now I have this sort. Now I can use it. Stuff like that. Sweet. OK, so let's do Fibonacci part 2, but this time with instantaneous machines. Yeah?
So the instantaneity is coming from, as a descriptor, is coming from what?
From the idea that information can instantly flow from the inputs to the outputs, whereas before it had this like delay. You have to absorb it into the state, and then the state changes, and then that causes the output.
So there's a simultaneity.
Yeah. I think of it as like when you have a dependency, information just like, it's like water flowing through versus like getting stopped in the middle. So, yeah, still open, yeah, to not set in stone yet at all. All right, so our plus machine, what did I say it's going to be? So we have, again, the interface is two things, one output thing. And the dependency is going to be this output port is going to depend both on that input and on this input. What am I going to fill it with? I'm going to fill it with no states. That's allowed this time. It used to be I had to have a state. And then my update, well, since I don't have any states, no update to do. What is my readout going to be? So it goes now from my state space, which is trivial, times my input space to my output space. And it's going to basically take x and y and output their sum. So this is really just now like a function. Great. All right, we can run that. And then I just wanted to show, sort of to check that this has the right thing. So this tells us, oh no, the dependency pairs. So 1, 1 means the first output is dependent on the first input. 1, 2, the first output is dependent on the second input. We can evaluate the dynamics. So given note the state, which is empty, and inputs 2 and -7, update the state. Well, there is no state, empty. And then finally the readout, again, given the state, no state, inputs 2 and -7, I get back -5. So it's doing what I said it would do. All right. Then we're going to do our delay machine. And in fact, every machine from before is one of these instantaneous machines. So I'm going to draw the same delay. And old machines had no dependency on the output of the dependency of the output on the input. So I'm not going to draw any sort of edges in here. Cool. OK. And now I'm going to wire them up like I showed on my screen. So we're going to send the output here, this thing here, and let's box that up. And so we can sort of think about, sorry, and then, yeah, so let's do the composition. We can think about what these things do. So if I put in a stream of like x's here and y's here, what does this thing do? It delays it by 1. So I sort of get y of t minus 1 coming out here. And then this guy adds it together. So we get x of t plus y of t minus 1. So you can think about that should be what happens to this machine. And then also, whoops, what is the dependency? So you can sort of follow it backwards. We see, what is this dependent on? Well, it's dependent on this port, which gets wired to here. So I have a dependency between these two guys. This one's also dependent on this, but this isn't dependent on anything. So I don't have the dependency here anymore. It's modulated by that state. All right, so we can sort of check.
Sorry, so
yeah.
why this isn't dependent? I mean, isn't the y of t still being used? Oh, sorry, I lost why the dependence stopped.
Yeah, so it's really an instantaneous dependency. And one way to sort of see it is what's going on in this box. We have a state u that's getting set to be this thing. And then u outputs this one. And so
putting the delay there stops the dependency somehow?
yeah, it stops the instantaneous dependency. I agree that like what you put in here will affect what comes out here, but not at a single moment.
I see. Okay, thank you.
Yeah, so if we run it, we do see sort of like x of t plus y of t minus 1 is 1, 3 plus 5 is 8, 4 plus 5 is 9. Seems reasonable. All right, and then we can, oops, I guess I did not program this, but you can also turn this into Fibonacci by adding in another delay. And the output of that delay is going to get sent to the two things. And it's going to be fed by this guy. And that would give us Fibonacci. We sort of have these two delays, and then we add together the results. Yay! And so finally, I want to show you, so the problem, one of the motivating things was this like multi-city thing. I don't want to copy people. And so we now have a solution for that. So to sort of this pattern, I'm going to add in this thing called fork, which takes in an SIR population and then puts out two of them, two copies of it. One which gets sent to city 1, one which gets sent to city 2. And what are its dynamics? So again, it takes in 3 things, it outputs 6 things. And given the input, it has no state. Given the input, it sends half of the input out this way and half of the input out that way. So it's forking the population. We can now do the composition and plot. And you're like, where did the pink go? And it's exactly under the green, because of course now the infections from city 1, cities 2, and cities 3 are happening exactly at the same time. So proof that everything works as it should. All right, so we will not have time for the final one, which is deeply interacting learning systems, which I hope are very tantalizing. But one of the punchlines is that we can build right now we can build a 1 neuron neural network and train it, which is pretty cool. And then in the future, hopefully we'll be able to build actual neural networks and other cool learning things. But let me skip to the end. And I do want to acknowledge, like, this work would absolutely not be possible without all of the amazing core Algebraic Julia team members. And then here are some resources. And then, thank you.
Great. Any questions for Sophie?
Very neat, very neat.
Thanks.
Do you see the fact that we have plenty of connections to the stuff that I've been talking forever and what you've been talking now, right? I mean, in particular, even this business of not wanting to duplicate every human being is because, I mean, that's kind of one of the things about linear logic is the fact that you don't want to duplicate everyone.
Cool. Yeah. I'd love to learn more about it.
Pretty neat.
Where are you with DILS?
Oh, I should say, sorry, DILS is the work I've been doing with Chris Brown and with David, and yeah. Where are we? Well, we can train a 1 neuron network. Can I just show you? It's kind of cool. We have, I guess this won't be that cool. I don't know. So, yeah, sorry. So where we are is right now we can, here's like the true solution. Here's our system that's untrained. And then we can train it. Error goes to 0. And then when we do the same plot, we see now our network solution and the true solution are on top of each other. Wow. What's left? So we're hoping to do, first of all, getting like, can we get neural networks that have many nodes in them? But then also, can we pop in different systems? So you can think of, here we have, I don't know, maybe an example might be if I have sort of 2 networks that do like plus and x squared or something, and I feed those into something like this. Sorry, this picture. So this would be my learner. These aren't doing any learning. They're just outputting, given an x, I output x squared. Given 2 numbers, I output plus. And the question is, could we learn a sort of configuration of these that would output something like some different sorts of compositions of these. So could I learn x plus y squared, or could I learn x squared plus y? So these would be different configurations of these two boxes learned by this thing. Is an example of something that would be, but the dynamics, and then, yeah.
It kind of seems like you've implemented the top row of this for DILS. You implemented the top row of this for DILS and not the bottom row. Is that right?
No, we've done both.
Oh, okay.
Yeah. I think the thing, so what's missing? There's some, I think there's some fudging in what are the types, like, what do we say live on here? They're monomials of the sort like ry to the r or something like that, very bland, or it doesn't capture all the richness, I think. Yeah. I think also like figuring out what are interesting DILS to compose is an open problem, I think.
So you said you could learn like x plus y squared or x squared plus y. Does that mean you're learning the functional form? Or are you learning coefficients on like a fixed form? Or
so
those are often treated as very different kinds of things.
I'm going to draw a new picture, and then maybe you can ask your question again. So we're going to draw the microscope picture, which is like you're looking down this thing. So this thing becomes this outer box. And inside, we have a plus box, which takes in two things and outputs one thing. And we have this x squared box, which takes in its squares. And if I wanted to learn this, you know, I sort of want to learn this wiring pattern. And if I wanted to learn this, I'd want to learn, I guess this is this wiring pattern. And so the question is, can we learn these different types of patterns?
Yeah, it's interesting. I mean, I think that'd be really neat if you came up with a new method for doing that. Like, you know, people sometimes call things like this like symbolic regression or things like that. Like if you, it's usually considered to be quite difficult to learn like the functional form of something, as opposed to just like if you have like some basis functions and then take a linear combination of them.
And I guess one difference is that you can use gradient descent for a lot of, but how, would you try and use gradient descent or something similar?
That's the problem. Like that's exactly like, what do you use?
The classic thing that people try to do for symbolic regression problems are like evolutionary kind of algorithms, things like that. But that's, yeah, it's a very different approach because, yeah, the reason why symbolic regression is hard is that it's not obvious how to explore that space of functions in an effective way. So.
Why don't we thank Sophie again?